In today's problem, we set out to fly around the Sun. The star of the show is the Parker probe launched by NASA in 2018 on its journey to orbit our star. The magic of this problem is that simply by knowing the radius at perihelion and aphelion, we can determine the velocities at these points. So, let's get started.
Binnacle Project.
First and first, let's read together the statement. It says that NASA's Parker probe aims to study the solar corona for the first time. To achieve this, it follows an elliptical orbit around the Sun with an aphelion of 1.1 times 10 to the 8 kilometers and a perihelion of 7.6 times 10 to the 6 kilometers. Determine the semi-major axis of the ellipse and the time it takes for the probe to complete one full orbit around the Sun. And section B, the velocity of the probe and at the aphelion and perihelion of its orbit. And we are given as data the universal gravitational constant and the mass of the Sun. So let's get to it. The first thing we're going to do is to draw an ellipse. This is an ellipse that is determined by its two focuses. In one of them, I'm going to place the Sun. This is the Sun, and this is our Parker probe, okay? So now let me indicate two important parameters. The first one, the closest distance to the Sun, this point, is the so-called perihelion. Perihelion. And the furthest one, this other point, is the so-called aphelion. Aphelion. Right? And finally, the distance between the perihelion and aphelion is the so-called major axis. Major axis. And the other one, this distance, is the so-called minor axis. Minor axis. And here we are asked to calculate the semi-major axis. Semi-major axis. What are we going to do? We are just adding the distance to the perihelion plus the distance to the aphelion and divide it by 2. That's it. I've placed here the distances we are given in the statement. The distance to the perihelion, 7.6 times 10 to the 6 kilometers, and the distance to the aphelion, 1.1 times 10 to the 8 kilometers. And as I was telling you previously, the semi-major axis that we are representing this way, semi-major radius or semi-major distance, whatever you want, will be calculated at distance to the perihelion plus distance to the aphelion, that will be the major axis, but we are dividing it by 2 because we are asked to calculate the semi-major axis, right? So now it's time to use our calculator in order to do 7.6 times 10 to the 6 plus 1.1 times 10 to the 8, and dividing it by 2, we are obtaining 5.88 times 10 to the 1, 2, 3, 4, 5, 6 to the 7 kilometers. Easy, right? As I run out of space, I've erased the previous calculations, but I've placed here the result. The semi-major axis or semi-major radius is 5.88 times 10 to the 7 kilometers. Here you have it. Okay? And now we are asked to calculate the time it takes the probe to complete one full orbit around the Sun. The time it takes to our Parker probe to complete one orbit around the Sun. And it's time to introduce you to one of the most difficult movements in gravitation. Look, the thing you're going to learn only applies for circular orbits, okay? Circular orbits. I know that our orbit is not circular but elliptical, but the conclusion we're obtaining through this way will be used in our elliptical orbit. Here we have a central mass, a star, a planet, whatever, and here we have a little satellite orbiting it. And what I want to explain to you is that what allows to this little satellite be here is the balancing of these two forces. One of them tries to pull it inward. This is the so-called the centripetal force. The centripetal force, that will be Newton's force, okay? The gravitational force. And this other one, the centrifugal force. Centrifugal force. And what are we going to do? We are balancing these two forces, okay? So, let's do it. This is the distance between the satellite and the center of the star, okay? Centripetal force must be equal to centrifugal force. The centripetal force in this topic will be Newton's force. And here you have it. G multiplying the mass of the sun or the star, whatever, multiplying the mass of the satellite of the probe, divided by the orbiting distance to the square. This is the distance. And this force must be equal to this one. The centrifugal force is determined by the mass of the satellite or mass of the probe, multiplying its velocity to the square, divided by the distance. Don't forget this formula. It's a typical formula for the centrifugal force. We can say goodbye to the mass of the probe. We can also say goodbye to the distance. And here we have an expression with the speed, with the velocity of our probe. And look, now there comes a very important happy idea. Look, the velocity of our body is the distance traveled divided by the time taken, right? Why don't we apply this idea to a complete revolution? Look, the velocity equals the distance traveled in a complete revolution, that is, the length of this circumference. The length of this circumference of radius d, that is 2 pi times the radius, 2 pi times d, divided by the time taken. And the time taken to complete a circumference is the so-called period. This is a very important idea because now we are using it here. We are substituting this formula here in order to solve for the period. Don't forget this movement. So let's do it. G multiplying the central mass, the mass of the sun or the central body, whatever, divided by the distance of the orbit must be equal to the velocity squared. That is 4p squared, the distance squared, divided by the period squared. And here we are solving for the period. But in doing so, let me show you a beautiful thing. Look, I'm placing here the period squared. Here I'm placing the distance cubed, and I'm placing the constant to the right side, 4p squared, divided by g and the mass of the central body. These are constants, okay? And here you have Kepler's third law. This is Kepler's third law, and I don't know if you can imagine the beauty of this result, because here we have Newton and Kepler with us. I tried to imagine Isaac Newton doing calculations based on his new theory and arriving at this point and feeling the happiness that when your theory embraces the previous one, means that your new theory is probably true. So, congratulations, Mr. Newton! But the thing we were doing to solve section A was solving this formula for the period. And here you have it. The period equals 4p squared divided by the gravitational constant and the mass of the central body, multiplying the distance cubed and the square root. But I told you a few minutes ago that these calculations was only for circular orbits, but our orbit is elliptical instead. So the only thing we have to do is to place the semi-major radius here instead of the distance of the orbit. And by using this result here, we will have obtained the period of our proof. So don't forget what we've done. This result, obtained from balancing the centripetal force and the centrifugal force, can be used in elliptical orbits only by replacing the distance of the orbit by the semi-major radius, and we will obtaining the period of our proof. If you use your calculator, and be careful because these quantities are awful, and replacing the distance with the semi-major radius, hope you obtain 7.78 times 10 to the 6 seconds, that is 90 days. That's it.
Binnacle Project.
And now it's time to solve section B, where we are asked to calculate the velocities at perihelion and aphelion. Look, this is the vector velocity at perihelion, and this is the vector velocity at the aphelion. And I've drawn it intentionally smaller than the other one because the velocity at the aphelion is smaller than the velocity at the perihelion. Now it's time for you to stop the video and try to think about how to solve it. Before stopping the video, let me tell you that as our orbit is elliptical, it is forbidden to balance the centripetal force and the centrifugal force. Please don't do it because our orbit is elliptical and it is forbidden to do that. So, what can we do? Even though our orbit is elliptical, what are we sure about? First of all, the conservation of the mechanical energy, that is, the mechanical energy at the perihelion, must be equal to the mechanical energy at the aphelion, right? And the mechanical energy at the perihelion is kinetic energy at perihelion plus potential energy at perihelion. That must be equal to kinetic energy at the aphelion plus potential energy at the aphelion. Now let's say that kinetic energy 1/2 times the mass of the proof, velocity at the perihelion squared, right? And the potential energy, -g, multiplying the mass of the sun, multiplying the mass of the proof, divided by the distance to the perihelion. Okay? And the same thing at the right side. Kinetic energy at the aphelion, 1/2 the mass of the proof, multiplying the velocity of the aphelion squared. And now the potential energy at the aphelion, that is -g, multiplying the mass of the central body, multiplying the mass of the proof, and divided by the distance to the aphelion. Here we can cancel out the mass of the proof as it appears at the 4 terms, and the rest of the magnitudes are known. And here we have the velocity at perihelion and the velocity at the aphelion. Now we need another equation to form with this one a system of 2 equations and solve it for Vp and Va. So what other magnitude remains constant in this topic? The angular momentum. Look, the angular momentum at the perihelion must be equal to the angular momentum at the aphelion. The angular momentum is defined as the cross product between the position vector at the perihelion, and this is the position vector at perihelion. Position vector at perihelion. And the linear momentum. This is the linear momentum at perihelion. And don't worry, because the linear momentum is defined as the mass of our proof multiplying the vector at the velocity vector at perihelion. Okay? The same way, the angular momentum at the aphelion is defined as the cross product between the position vector at the aphelion And this is the position vector at aphelion, position vector at the aphelion, cross product, the linear momentum at the aphelion. And the linear momentum is defined as the mass of our proof multiplying the velocity vector at the aphelion. Right? Please don't stop the video and don't be scared with this mathematical treatment. We are not diving into it. Look, the only thing you have to understand is that the angular momentum, the magnitude of the angular momentum is the distance to the perihelion. This is magnitude. I'm not working with vectors anymore. The mass of the proof, the velocity at the perihelion, and the sine of the angle between the position vector and the velocity vector. And the angle between the velocity vector and the position vector is 90. So this equals 1. Easy, right? And the same thing at the right side. The distance to the aphelion, the mass of the proof, the velocity at the aphelion, and the sine of the angle between these two vectors, the position vector and the velocity vector, which is 90 degrees. And also the sine of 90 is 1. We can also cancel the mass of the proof, and here we have another equation, radial distance to the perihelion multiplying the velocity at the perihelion equals the radius or distance to the aphelion and the velocity at the aphelion. And this is the second equation that we're using with this one in order to solve for the velocity at perihelion and velocity at aphelion. As I run out of space, I will erase the previous calculations, but here we have the results we obtained using the conservation of the mechanical energy and using the conservation of the angular momentum. We are solving for Vp and Va, as the rest of the parameters are well known thanks to the statement. Okay? What can we do? Why don't we solve here for Vp equals Va divided by the distance to the perihelion, and let's substitute this expression here, and we are obtaining 1/2. Now the velocity at the perihelion but squared, that is the distance to the aphelion squared, the velocity at aphelion also squared, divided by the distance to the perihelion squared, minus g, the mass of the Sun, the distance to the perihelion, equals 1/2 the velocity at the aphelion squared minus g, the mass of the Sun, and the distance to the aphelion. Now it's time to bring the terms that contain Va to the left. 1/2 distance to the aphelion squared, velocity of the aphelion also squared, distance to the perihelion squared, minus 1/2 the velocity of the aphelion squared, equals, and let's throw the terms without Va to the right, that is this one but in positive, g, the mass of the Sun divided by distance to the perihelion, okay, minus g, the mass of the Sun, and the distance to the aphelion. In order to solve this equation for Va, it is time to take Va squared, take it out, and we are obtaining velocity at the aphelion squared, 1/2 the distance to the aphelion squared divided by the distance to the perihelion squared, minus 1/2. Okay, we've just taken it out. At the right side, g, mass of the Sun, distance to the perihelion, minus g, mass of the Sun's, distance to the aphelion. And now it's time to send this term to divide to the right side, and we are obtaining VA squared equals G, the mass of the Sun, and the distance to the perihelion, minus G, the mass of the Sun, and the distance to the aphelion, and the parenthesis, 1/2, distance to the aphelion squared, distance to the perihelion squared, minus 1/2. And finally, square root. Please be patient because it's time to use calculator. In order to help you with this awful calculation, I've placed here the partial result obtained in the numerator of this fraction, 1.62 times 10 to the 10. And please be careful because you can see that the distances at this segment are given in kilometers, so don't forget to multiply them by 1000 in order to put them in meters. And here you have this, the partial result obtained here, 104.24. Now we can do together the final result for the velocity of the aphelion, that is 1.62 times 10 to the 10th divided by 104.24 and a square root of the result, and we are obtaining 1.25 times 10 to the 4, 1, 2, 3, 4 meters per second at the aphelion. And by introducing this result here, we are obtaining the velocity of perihelion, that is distance to the aphelion, 1.1 times 10 to the 11, not 8, but 11 in order to put it in meters, multiplying 1.25 times 10 to the 4th, divided by the distance to the perihelion, 7.6 times 10 to the 9th, not to the 6th, to the 9th, in order to put it in meters. And we are obtaining 1.81 times 10 to the 1, 2, 3, 4 to the 5 meters per second. And that's it. In this video we worked with an elliptical orbit, and don't forget that this is the major axis, this is the minor axis, and this is the semi-major axis, and is the parameter used using the Kepler's third law in order to obtain the period of our proof. And we also used the conservation of the mechanical energy and the conservation of the angular momentum in order to obtain the velocity of the perihelion and the velocity at the aphelion. At this moment, I'd like to clarify the concept of angular momentum and its implications for the motion of planets. Look, angular momentum is a relationship between the position of a particle rotating around a point, the velocity it has at a given instant, and the angle formed by both vectors. It turns out that, according to Kepler's second law, angular momentum is constant at all times. What this implies is that when a body is rotating, it will try to keep its rotation stable precisely to maintain angular momentum constant. And that's what you can see in this video I brought you, kindly provided by the Faculty of Physical Sciences at the Complutense University of Madrid. You can see that when the wheel is spinning, it resists falling, meaning it tries to keep its motion stable. I know there's a rotation called precession, but that's not important right now. What I want you to understand is that thanks to the conservation of angular momentum, the orbits of planets are stable. Otherwise, the planets would enter unstable motions that would eventually eject them from their orbits. If today we are orbiting harmoniously around the Sun, it's, among other things, thanks to the conservation of angular momentum. So repeat after me: long live the conservation of angular momentum, and also long live the conservation of energy. I hope you found this problem enjoyable and that you can apply these concepts to future problems, so you can soon master universal gravitation. See you soon! And now, watch a theory video if you think you've gotten lost in some aspects, or skip to the next exercise to continue climbing. And as always, like, turn on notifications and comment. See you soon!